always my pleasure to present my work in my country among the youth of my country. So it's very interesting what Dr. Majd mentioned in the beginning about the cost of desalination, which really hindered the desalination processes worldwide. I'll just start with two facts. 70% of our planet is water, but 98% of that water is inaccessible water. That means it's highly saline water, like in the oceans. And the funny fact, among the fresh water that is we producing or having, only desalination contribute only by 1%, which is quite shocking. I remember one of the best quotes in desalination, it's for JFK. John F. Kennedy stated in 1961, if as a human being, we could desalinize water with low energy and low cost, this on the long term will dwarf any other scientific accomplishment, including our landing on the moon. That's the vision we need, because water is very important for industry, for agriculture, for living standards. Simply, we cannot survive without water. And 80% of that water is saline water, but we can desalinize only 1% due to the technical and economical challenges of the current desalination processes. So I will just present to you my work, which was, this introduction was the driving force behind this work. And my work is titled by Novel Solar Desalination Technique Using Novel New Membranes by a New Technology that is named Membrane Distillation. I'm the inventor of this technology, and I work as an associate professor in the chemical engineering department at the University of Jordan, as well as I got the chance to develop my patents into a commercial product. And we've just now finished the development process, and we're gonna go to the market in Saudi Arabia, because Saudi Arabia, 60% of the desalination plants are located in Saudi Arabia. So I'm currently the Chief Technology Officer at the Saudi Membrane Distillation Desalination Company, which is incubated inside the University of King Abdullah University of Science and Technology in Jeddah, Saudi Arabia. I will start with you with why did I choose membrane distillation. Matter of fact, sometimes your destiny chooses you. You don't choose your destiny. I started my master's in Jordan University of Science and Technology under the supervision of Professor Banat. And Professor Banat gave me the choice of working on currently employed techniques, which is an easy thesis, or a tough thesis to work on a new technology that it has many skepticals and a few believers. So I chose membrane distillation. And when you start a new field, you start with where everything have started. And everything have started in 1964 by Bodel. He filed the first patent in membrane distillation. And the first published paper was in 1967 by Professor Findlay. But I have here a paragraph of the first published paper by Professor Findlay, where he said that we could desalinize water by evaporation through a membrane. Before I start, desalination classified into two different techniques. Either you use the phase change, which include evaporation and then condensing and recovering, or you use membrane, like reverse osmosis or electrodialysis and so on. Membrane distillation is a hybrid between both. There is a phase change and there is a membrane. But the most important thing, that you don't need to boil the water. You don't need to heat up the water to the boiling points to get the vapor out of the water. In applying membrane distillation, I will just go through the concepts more precisely in the next few slides. But I read this patent and this paper to achieve the membrane requirements here, to achieve this process. The membrane should have a high resistance to heat flow by conduction, so you don't lose a lot of heat because it's your driving force. The membrane should not have an excessive thickness, because the thicker the membrane, the higher the resistance and the lower your flux. Flux means the water production rate. Negligible permeability to liquids. That's a very important condition, because the idea of membrane distillation is the membrane should not be wetted with liquid whatsoever. The membrane pore should be dry all the time. High porosity. low absorbability of moisture, and a uniform thermal conductivity. And I will come back to this because in my research, I've contradicted this last requirement. You need high conductivity at certain region of the membrane and low conductivity at another region of the membrane. Now, I will go just through the concept. In the concept, we have the membrane, which acts as a physical support separating a hot feed solution from a cooler chamber. So, in our membrane distillation, the driving force is not pressure. In reverse osmosis, for example, you need to apply pressure that is higher than the osmotic pressure. You need to beat that force in order for your water to go through the membrane. But how the reverse osmosis membrane work? It works in a mechanism we call solution diffusion mechanism. What we mean by solution diffusion mechanism, just picture it as simple as that. You know, there is no pores in the membrane, so the membrane is not porous. It's a dense membrane. But the material of the membrane is made in a way that the dissolution rate of water molecule and the permeability rate of the water molecule is 10,000 times higher than that of the salt molecules, which means there is chemical interactions between the membrane matrix and your feed. In membrane distillation, the membrane is porous, so you don't need to bother with the fouling issues, with the chemical interaction issues, because the mechanism of separation is quite different. The mechanism of separation is that those pores are dry, and this membrane is made of a hydrophobic material. What we mean by hydrophobic material, a material that does not like water. So water in the liquid phase will never be able to pass through the membrane. Only water in the vapor phase can pass. How we can achieve that? By applying a temperature gradient. So we could evaporate the water at very low temperature, even at 40 degrees Celsius. As long as you have delta T, a driving force, a thermal gradient between the feed side and the permeate side, then this is enough to generate a chemical potential gradient across the membrane matrix, and the water vapor will migrate from the hot side to the cold side. Water evaporates, salt does not evaporate, and that's how the separation is achieved in our membrane. This is the technology, and it has many advantages. You have 100% rejection of all ions, macromolecules, colloids, cells, any non-volatile matter. Lower operating temperature because you don't need to heat the water to the boiling points. And there is no pressure involved. You don't need electricity to have a high pressure pump in order to force the water to go through the membrane. Reduce vapor spaces because in the distillation tower that is 60 meters higher, you substitute that vapor liquid equilibrium area by a very narrow pore. It depends on the thickness of your membrane, which is around 100 micrometer. So space-wise, it's good. Temperature-wise is good. Energy-wise is good. Separation-wise is good. But now I ask my professor the big question, why this process is not commercialized yet? Because, of course, there is advantages or disadvantages or drawbacks. And those disadvantages, as I've mentioned earlier, the membrane pores should be dry all the time, no liquid go through. One of the problems is the membrane wetting. Another problem is low permeate flux. The water production rate is quite low, and the high cost of the membranes for membrane distillation. Those all are result of the inadequate design of the membranes. If you go to any company now, ask them to buy a membrane for membrane distillation, simply they don't manufacture and they don't have. So as a researchers, we were only focusing on the membranes that is of a hydrophobic nature. We're buying a membrane that's for ultrafiltration or microfiltration, apply it in membrane distillation, publish the paper, and everybody is happy. But this has never helped membrane distillation into getting into the market because the pores of those membranes were quite large, 1 micrometer, 0.5 micrometer, so the water easily can wet through the membrane. And their life durability will be influenced by that, and their flux was around 8 to 10 liter per square meter per hour. On the other hand, when you talk about reverse osmosis, you talk about 35 liter per square meter per hour. Now, the research in membrane distillation started to be using those commercial membranes available in the market. As you can see, the pore size was ranging between 0.2 microns to 1 microns, and porosity 80, 70, and it's made of a hydrophobic material like polytetrafluoroethylene, polypropylene, polyvinyl difluoride, and so on. So those are the membranes which caused an issue in membrane distillation, hindered membrane distillation from going into the market. And I've started in my PhD, after I finished my master's, about a new concept, a new design for the membrane. What we thought about is to design a special membrane that is made specifically for this process. So we looked into the requirements. What are the requirements of the membrane? We redefined the requirements that has been proposed by Findlay and Bodel in the 60s. And we found that the membrane should be highly hydrophobic to reject all water and no wetting problem is occurring. And this requires the pore size to be as small as possible. On the other hand, the pore size should be larger to reduce the mass transfer resistance for the water flux. The membrane should be as thin as possible to reduce the barrier resistance to mass transfer, and it should be as thick as possible to reduce the barrier resistance to heat transfer. So you can see all the requirements are mutually contradictory. What we thought about a solution. And this solution is coming by designing a hydrophobic hydrophilic membrane. From one side, it doesn't like water. From the other side, it does like water. And this hydrophobic hydrophilic membrane is made of a very, very thin hydrophobic layer and a very thick hydrophilic layer. We believed that this design will revolutionize the membrane distillation process, because the top hydrophobic layer, which is very thin, it will prevent the penetration of the liquid water through the membrane. On the other hand, the resistance to mass transfer is minimum because this layer is very thin. The heat conductance can be reduced by the hydrophilic layer because both hydrophilic and hydrophobic contribute to the heat transfer, while only hydrophobic contribute to the mass transfer. That was the concept of our design, but now we need to manufacture such a membrane in a single casting step, because when you go to industry, and this all membrane people sometimes don't notice, we work in our lab in an easy way. We can coat, we can plasma etch, we can do 3D printing, but when it comes to scale up, it's a different story. In industry, you need to cast the membrane in one single step. So we thought about having a polymer that is we make ourselves, and this polymer is very hydrophobic. We mix it with the hydrophilic polymer in one solution. So in both solutions, you have the hydrophobic polymer, the hydrophilic polymer. Then we cast, but the hydrophobic polymer has a lower surface energy. So it migrates to the top surface, making the top surface hydrophobic and leaving the bulk of the membrane hydrophilic because it has lower surface energy. So, and it can be dissolved with the hydrophilic polymer in the same solvent. And then when you cast, the hydrophobic polymer will just migrate to the top surface by the thermodynamic forces. Now, we finished this and we registered the first patent, finished my PhD, everyone is happy. But then I started thinking about, because when you open a venue of research, there is a huge doors open for you. So you can explore, and you are the initiator of the idea. And we thought about doing some mathematical modeling to predict the membrane performance. And I found out that the hydrophilic layer has a significant effect on the membrane performance. In the beginning of my life, in the first papers even I published, I was talking that the hydrophilic layer does not have any resistance to the mass flux. But when I did the mathematical modeling, I found no, it does contribute, especially with the thermal conductivity. If you can see this figure on the right-hand side, you can see that the flux is jumping 3 to 6 times as we are moving in the x-axis if we increase the thermal conductivity of the sublayer only. So this opened the door for another membrane design, and this membrane design included nanoparticles to be implemented in the dope solution, and it will be cast on the same step. Now, we achieved this by implementing metallic nanoparticles inside the hydrophilic layer. Now, we achieve this either by utilizing the evaporation time. After we cast the membrane, we leave it for a few minutes, so the nanoparticle will settle down, but the surface modifying macromolecules or the hydrophobic molecules will migrate to the top surface. But again, evaporation time is not an option in industry because the casting machine should be running in a capacity of 15 meters per minute without any stop. So you just can't stop. So we thought about another idea, which is coating of the hydrophobic layer on the top of the hydrophilic layer. And we achieved this by designing this machine. In this machine, it has, the casting machine. You have a rolling papers that is going through your machine. and you can cast by using a doctor knife in order to determine the exact thickness, and then we coat by what we call a slot die. So the thickness of your coating can be really controlled, and by this way we guarantee that all the hydrophobic polymer are on the top surface and those nanoparticles molecules are on the bottom surface. So that was the concept. Now, of course, the membrane is the heart of the process. If you design a good membrane, then you're good enough. But again, you need to go to the industry. So we designed again a module for the membrane, and this module is a plate and frame module, and now we are using a spiral wound module for our process. The good news is we finished the development process, the scaling up, I mean. We took this product from the laboratory scale into the commercial level. Of course, there was some private investor who invested money on the patents and the protection of the intellectual properties. And now we finished the development process, which means we could produce the membrane on large scale with a very good quality and a very consistent quality. So the first batch and the second batch and the third batch and the fourth batch give you the same performance. And this is very important from industry point of view. We send the membranes for testing for a Dutch company, because when you register a patent, you need what we call a third-party approval. Somebody that is completely outsider, but he's in the field to test your membrane and prove that your claims, what you claimed in your patent, are correct. And this Qtaishat company in the Netherlands, they did this for us, and they were very happy with the performance, and they made the first order of the membrane from our company. Now, for my performance point of view, I've reached a flux up to 140 liter per square meter per hour, which is 4 times higher than the reverse osmosis membrane. We have a series of patents between 2012 and 2019. Those are the countries we chose to file the patent at, because you can't just patent everywhere in the world, because you're going to lose a lot of money. So you have to be very picky where to file your patent, which countries, and we chose the countries that could be competing us in manufacturing membranes. USA, Japan, China, Australia, South Korea, and Singapore, those are the countries we chose. And the green highlighted, that means the patent rights are granted for us. The yellow one is still under examination. The last patent was filed in 2019. It's just been published like 2 weeks ago. So now, it's important to talk about the investment. We have a total investment so far of $5 million. The membrane customers that we will be selling for, Qtaishat in Netherlands, Memsis in Germany, and Philos in South Korea. And we are collaborating with Membrane Solutions in China to manufacture the membrane as well. I'll show you some pictures. This on the left-hand side bottom, this is a portable desalination unit that can produce 25 cubic meter per day, and it can be anywhere in the world without electricity by using solar energy. So this is a truck that have the membrane modules. On the top of the truck, we have solar cells, solar collectors, in order to do the desalination process. And that's myself working on the machine of the casting of the membrane. So that's, I believe, everything I need to say. Now, in conclusion, our membrane seems very promising for future commercialization of the membrane distillation processes. The membrane with the highest hydrophilic layer conductivity and the thinnest hydrophobic layer produce the best performance. Module design is as important as the membrane design in membrane distillation. And finally, I would like to thank you all for attending this presentation, and I'm ready for any questions if any.